The evolution of cities is built upon the interaction of people. People meet friends or strangers on streets, buy goods from markets, or collaborate to form enterprises. The urban-built environment is the arena where these interactions take place. One of the primary challenges of good city design is therefore to maximize interactions between people and places while minimizing friction. Contemporary cities generate volumes of data that offer unprecedented opportunities to address this challenge. These data can help us understand how the human interactions that cities facilitate can deliver social, economic, and environmental rewards. Many urban activities can be shown in numbers by counting purchases in stores, tallying traffic on streets, tracking real estate transactions, or following business location patterns. In addition to social activities, cities also have physical infrastructure, which can also be abstractly represented. A complex built environment can be reduced to three basic elements: links, representing paths along which travel can occur; nodes, representing the intersections where two or more paths cross and public spaces form; and buildings, where most human activities take place and where the movement of people, goods, and information begins or ends. This framework allows us to describe spatial relationships between people, places, and institutions using powerful network analysis methods. How can we use this method to describe a city? The reach metric, for instance, characterizes the number of particular destinations that can be reached from any location in a city within a given access radius. If the destinations describe the number of residents, then the metric tells us how many residents one can access around each building. We can specify a similar measure for the number of jobs in each building, or floor areas, and perform the analysis with a different network radius, depending on what mode of travel we assume the trips to take. If we add up all these travel costs to individual destinations, then we can also determine the closeness of each location, which forms another metric. Or consider the betweenness index, which estimates how in between other locations a building is. If we know that in the morning peak hour commuting occurs from subway stations to office buildings, then the betweenness index can estimate the trajectories that such trips are likely to take and tell us which buildings are passed most often along the way. The different specifications of network analysis yield a series of results describing proximities and adjacencies between people and places, which can be important for locating a business, explaining traffic patterns, or the value of land in different parts of a city. In Cambridge, Massachusetts, for instance, there are roughly 15,000 buildings, and to calculate any of these metrics requires exponentially as many more calculations. It would be impossible to calculate these indices manually. That's why we are introducing the Urban Network Analysis Toolbox that is designed to automate these calculations on a computer. The toolbox is built on top of the GIS platform, which allows us to easily combine urban network analysis with other types of data and spatial analysis approaches. Urban network analysis can describe complex spatial problems and help us address fundamental questions of good city design. Can the layout of a city facilitate equitable access to the city's resources? How does the form of a neighborhood affect the economic performance of its enterprises, or our perception of its quality, its livability? Urban network analysis offers a useful framework that allows different professionals to describe dense urban environments with clarity and precision, and thereby address a critical step in developing a better understanding of how we shape our cities, and how they, in turn, shape us.